So welcome to this lecture. This will be about Contiki and Kuja. Well, we have already seen a little bit of Kuja. Anyway, we will just see it again. This is basically the last lecture on, let's say, hands-on activities. So we close today. Sorry, if you are studying for another subject, you can go outside, please. Or you can just please be quiet or go in the last rows maybe. Thank you. So this will be the last lecture for what concerns operating system for wireless sensor networks, and so we will close basically today all the topics, and then next time we will talk about the projects. So I will present the projects, enter into the details of the 3 projects that are on the website. And yeah, that's it basically. Now I'm sorry, but this set of slides is not online yet. I've sent a copy of them to Professor Cesana, but unfortunately we hadn't the time to put them online, so we will do it as soon as possible, okay? Together with a Contiki example that we will see today. Very good. So we can start, I guess, if you do not have any questions at all. Okay? Good. So, what's Contiki? Well, again, we are talking about operating systems. We have seen TinyOS, we have seen Motrunner, and today we will see Contiki. We will see Contiki, which is another operating system. Okay? More or less, it has the same set of features and requirements that also TinyOS and Motrunner had. So it's an open source operating system for wireless sensor networks, highly portable, meaning that it supports several different hardware platforms for being installed to. A difference, I would say, with respect to what we have seen so far is that TinyOS supports multitasking. Okay, so we will see that we have this feature, which is the proto-thread feature, which basically allows the programmer to create processes and basically processes which are similar to threads, so that you can have multi-processes in your application. Again, the developers of Contiki claim that it is a memory efficient and energy efficient operating system, so it's suitable for sensor networks and in general for resource constrained hardware. Typical configuration for the hardware is again very, as you can see, resource constrained. So 2 kilobytes of RAM memory at minimum, okay, and 40 kilobytes of ROM memory to store libraries, core code, and application code. Okay, so you see we are in the range of requirements that we also saw for the other operating systems. So something very, very, very resource constrained. Now, one thing about Contiki is that it has been used, actually with success, in many commercial products, I would say. Now, I was wondering why, because if you look at the timeline, Contiki comes after TinyOS. Okay, so probably one of the first famous operating system is the first famous operating system is TinyOS, and Contiki comes just after. But if you look at the commercial products that are available in the field of the Internet of Things, many of them use Contiki, and I was wondering why. Okay, and probably one thing is that in Contiki you have already implemented a set of libraries which can be used for communication, and as we will see, you have the, let's say, TCP/IP stack, or at least a lightweight version of the TCP/IP stack already implemented, and it's called the micro IP stack. So basically, you can use your sensor network operated by Contiki to communicate with TCP/IP. Okay, so you basically build on top of the 8.2.15.4 MAC all the stacks for communication with IP and TCP. Okay, so reliable communication, requests for missing frames, EP addresses. Okay, all this kind of stuff. Of course, when the complexity of your application does not require to use the complete TCP/IP stack, Contiki gives you the possibility to use, let's say, even lighter networking stack, which is called RIME. We will see it, and which provides basic communication capabilities like reliable unicast, broadcast, and this kind of networking primitives. So probably one of the, let's say, main features for the success of Contiki is that it comes with a set of libraries that you can use off the shelf to build an application which can be used in a commercial environment, I would say. And just to give you some examples, if you go on the Contiki website, which is the one from which you download the system and you download actually also the virtual machine, you have a banner here basically with all the applications, or let's say with a selection of the applications that you can find out there. So for example, you have, let's say, let me see, this one, which is let's say home gateway for home automation applications, which is based on Contiki. So you can attach different sensors to this gateway, like lighting sensors, energy consumption sensors, thermostats, this kind of stuff. Everything is operated by Contiki, and you can build basically a home automation system by yourself. Okay, this is based on Contiki. There have been also application for, let's say, the environment monitoring, like badgers tracking. So they made a research study using Contiki. They built basically these trackers for badgers to see where these animals were going, and if there were some patterns in their movements and this kind of stuff. You have tools based on Contiki for energy optimization of data centers. So again, basically current sensors which are then operated by Contiki for transmitting their measurements to a remote place where you can analyze the energy consumption. Another example is the radiation monitoring. Okay, so it's a radiation, basically a Geiger sensor or radiation sensor that can then communicate through Contiki. So again, enabled by Contiki with other devices. And as you can imagine, Contiki has its own cloud service, which is this one, the ThinkSquare. Now by doing this, we are going back to the first lecture, basically, of these hands-on activities, where we saw Savly and Sixth Sense. Now also Contiki has its own, I would say, cloud service for storing data and accessing and analyzing data, which is called ThinkSquare. Okay, so again, in this case, it's a closed service, so you cannot register to it, but you have to request a demo if you want to test it, and it will come with a cost, probably. Okay. Now, oops. Now, other important features of TinyOS, of Contiki, sorry, are that we can use it to, we are not constrained to run one application on top of it and then to redeploy all the sensor network when we want to change maybe one parameter or change the application. But similarly to ModeRunner, Contiki allows you to dynamically load a new process on top of it. Okay, so again, we have a difference with respect to TinyOS. If you remember, in TinyOS, you build an application by gluing together low-level components, and then you deploy the application. So basically, the operating system is glued with your application in one single piece of software that then you deploy on the hardware. While we have seen in ModeRunner that there is a clear division between the operating system and the processes. Okay, so the operating system is always running, and then you can load assemblies on top of it. In Contiki, you have a similar setup as you find in ModeRunner. So you have a core set of libraries and routines which are running on top of the mode, and then you can load on top of it an application. Okay, so that you can remove the application while still maintaining the core features. Okay, you don't have to redeploy everything. And as I was saying before, Contiki supports multi-threading, or at least a very, very simple form of multi-threading, which is implemented as an external library, meaning that if your application needs multi-threading, then you have to request it as an external library. So multi-threading is not a feature of the operating system itself, okay, but it's a feature of the application, meaning that if your application needs multi-threading, then you have to write it and compile it by properly requesting for multi-threading support. Okay, this is of course for optimizing and resource efficiency. Okay, if you do not need multi-threading, then why inserting multi-threading in your application, right? So from a certain point of view, let's say, I would say that Contiki try to fuse together the good features of TinyOS and ModeRunner in some sense, okay? Of course, we have also some cons, okay? And probably first, the main cons is that the documentation is rather scarce again. So in order to really learn how to use Contiki, you actually have to go inside the source code and see what's happening, how to use particular components. You have to, spend a lot of time working on it. Okay, it's not something that you can learn just by reading a set of slides or reading a web page. You actually have to download the source code and try and make a lot of mistakes and then learn actually something. At least that's what I did. Okay. Now let's see very, very quickly a system overview. So as I was saying, the concept is a little bit different from TinyOS, and I would say more similar to ModeRunner, even if we do not have a virtual machine here. Okay. So I would say both the ROM memory, so the part where the code is stored, and the RAM memory, so where the part where the variables are stored, are divided in two parts in Contiki. Okay, so we have a core part which stores the information for the operating system, and then we have a part which is free for your processes. Okay, so and that's basically it's the part that you modify when you dynamically load a new process. In the core, so the part of memory that remains, I would say, untouched, you have the kernel, which is basically a piece of code that directly works with the hardware, which is underneath. And in this case, you don't have a hardware abstraction layer, such as in ModeRunner. So the kernel directly allows your application to basically use the hardware underneath. Then we have a set of libraries and a piece of code which is called the program loader. Okay, so which basically takes care of managing your application. So loading your application, allocating the proper memory for the variables of your application, running the initialization routines, if there are any. And then on top of this core system, you have a set of processes, so which can be services and applications. Now, services and application are basically two different things, because you have to think that the application is what you write. Okay, so basically the top level software that actually implements the logic of your application. But your application may use services which are already provided. As an example, the communication stack. Okay, so first I have mentioned this micro IP stack and the RIME stack, which are two communication primitives that you can use in Contiki, and these two are implemented as services. Okay, so are different processes that you have to include in your application in some way. And of course, if you do not need this kind of processes, these are not included in the application. Again, memory efficiency. And this is exactly what I was saying. Okay, so a service is a process that can be used by other processes, and it's to some extent it's some sort of shared library. Okay, that you load and other processes can use. Examples are the communication protocol stack, or the drivers for communicating with the sensors, or maybe algorithms for handling data. So you may want to implement a service for example, computing, I don't know, the mean of vectors of numbers, or the Fourier transform of a vector of numbers, or other complex operations. And instead of copying and pasting basically the source code in all the points of your application, you just write a shared library, so a service that you can access at any point for running these functions. And of course, these services can be replaced. So if you come with a new version of your library, then you can replace it just as you replace an application. Okay. So the program loader will also manage services. Now, in the core part of Contiki, we have, as we said, the kernel functions, the function for talking with the hardware, and then we have a set of libraries, of course. And the set of library which is included in the kernel includes only the most used libraries. So, for example, routines for moving pieces of data, like memcopy and this kind of stuff, are included in the kernel. But other routines, for example, the rarely used ones, like the one for converting characters to integers or this kind of stuff, must be included ad hoc. So you have to include the proper file when you implement an application. Okay. So some libraries are already included in the kernel. Some others are to be included manually, I would say, when you write an application. Now, multi-threading. If you think about how the kernel of Contiki is structured, it is similar to TinyOS. So it's event-driven. Okay. So if you remember a TinyOS application, basically the workflow is driven by events. Okay. The starting point is an event, the boot.boot event. You have timers that triggers events. You have the receive event when you receive a message. So everything is basically driven by events that are, fired by the operating system. And you don't have multi-thread. What you have is tasks, basically, in TinyOS. So you can reply to an event either by running some code or by posting a task into task queue. Instead, in Contiki, there's always this sort of event-driven workflow, but you have also the support for multi-threading, okay? Meaning that you have actually different processes that you can write and you can run simultaneously. It's not like proper threads in a standard PC environment, but in Contiki you have this sort of proto threads. Now, for what I have understood, the difference between one of these proto threads and a standard thread is that if you think about threads, you have a separate stack, so a separate part of memory which is allocated to each of these threads. Okay, so when you write an application which is composed by several threads, each thread has its own memory space. Okay, and you cannot go from one memory space to the other one. But of course, maintaining different part of the memory is costly. So this feature is not implemented in Contiki, and all the threads have the same. So basically, they share the same memory. Okay. This can sometimes be a little bit difficult to maintain because you can have race conditions. You can have that one thread writes on a variable and the other one, while the other one is reading the variable. So it's a little bit tricky. Okay. But by implementing these proto-threads in such a way, of course you save resources because you do not have to maintain separate stacks, one for each thread. And if you think about the simplest application that you can write in Contiki, well, that is a proto-thread. Okay, so one application is a proto-thread. So it can be either a single proto-thread or it can be a collection of proto-threads. So several of these proto-threads that run. We will see an example. So again, easiest way to learn it is to see an example. Now, there are some macros that you have to use in Contiki in order to declare these proto-threads, which basically are the atoms of your application. So you define a proto-thread like this, define process, and you define either a name, like a local name for a variable, and a name in form of a string that then can be printed. And then you have to declare the start of a process and the end of a process, and this basically defines the scope of the process. So all the code which is inside these two macros, process begin and process end, defines the logic of your thread. And then there's the body of a process. So actually, between begin and end, you have a process thread which contains all the logic. We will see now some examples. You have other macros, for example, the auto start process, which tells the Contiki core system which is the process which starts at the beginning of the application. So it can be one, it can be more. Okay. And then inside, to control the workflow inside each thread, you have this kind of macros like process wait. So these macros will block your process and they will wake the process again when something happens. Okay, and you see that this is a little bit different from TinyOS. Okay, because in TinyOS you don't have to explicitly inform the scheduler when to stop your application. Okay, you just have a set of events and a set of tasks or commands that you run in response to these events, but you don't have to explicitly say to stop your process. Okay, instead here in Contiki you have to do it. So you have to specify, okay, I'm at this point, wait until a timer expires, wait until the sensor have read the measurements, or wait until that measurement is above a certain threshold. Okay, so the programming style is a little bit different, and again, one of this is let's say some sort of, it depends on the taste of the programmer. Probably maybe one is more suited to using TinyOS, maybe another one is more suited to this kind of programming and prefers Contiki. Okay, we maybe go to the documentation and see other of these macros. If you go, of course, if you go on the Contiki website, you have the documentation, which again, you find mostly everything, but it's not very well explained. That's why I say it's a little bit scarce. Okay. For example, let me see here. Where is it? It was under proto-threads. Contiki system, proto-threads. Okay, so here you have a series of macros that you can use, and you have a description for each macro. Okay, so if you're interested in using Contiki, then this is basically the starting point. Okay, coming back here. Okay. Now, this is the, let's say, simplest program that you can write in Contiki. Okay, so this is the Hello World application. So we have seen that you have to declare what is the process. So in this case, it's the Hello World process. This is, let's say, the local name, and this is the string name. We will inform Contiki that we want to start it at the beginning. So after, let's say, the kernel has prepared all the necessary routines. And then we have to declare the process logic, okay? So the process logic, which is between these two macros here, begin and end, prints hello world. Now we have to see what is the meaning of printing something on a mode, right? And then we have a while loop, so an infinite while loop, which just waits for an event. So basically, this application starts, prints something, and then just waits, okay, for something. Now, it is typical to have an infinite while loop in Contiki applications just because of this different style of programming, okay, in threads instead of, let's say, events that the operating system triggers and you have to manage. Okay? So inside this while loop, you have basically all the logic which is continuously executed. Now the printf here, if you think about, updating this code on top of a mode, it does nothing basically, because modes have no terminal, they cannot print anything. They are typically deployed somewhere, they have wireless communication, but they cannot print. Now, this printf in Contiki is basically for using it with Kuja, okay? So when you print something in Contiki and you run the simulation in Kuja, you will see the proper string which is output in the terminal of Kuja, okay? So it's the equivalent of the dbg statement of TinyOS, when used with TOSIM. Okay, if you remember, in TOSIM you have DBG, you have to decide on which channel to output the print statement, and you will see it in the terminal. In Contiki you use directly printf. Okay, so it's much, I would say much more easy. And we will also see that by using printf we can also attach Kuja to Node-RED, so to the web, let's say, part of the Internet of Things in a very, very convenient way. Now let's run it just to try it. So let's open our virtual machine, open Kuja. It will take a little bit. Is it going? Yes. Okay, now, well, you're used to it, right? So let's create a new simulation and add a new mode type. I like to use the sky modes. And then when you browse here in the folder user Contiki minus 2.7, you have two basically folders, apps and examples, that you can try to run. Okay, each one comes with its own readme file. Okay, in this case I will open the Hello World application, and you have to select the source file to use. Okay, in this case hello world.c. Regarding the programming language, basically you use C here. Okay, it's you have these macros which are particular to Contiki, but the main programming language is C. Then you compile it, and this will compile the file and will produce an executable that then you can run. You type on create. In this case we have just one mode. Okay, and I can start the simulation. Now what I am expecting to see is just a hello world which is printing here, okay, on the mode output window. Okay, so in this case we have also some other informations here which are basically coming from another service which is loaded, which is the RIME communication protocol. Let me just open the source file, which is there. Where is it? This one. Okay, so this is how it looks like. You have to include Contiki, which includes all the libraries for the system, stdio for printf, and this is one of the libraries which are not included in the core. Okay, so if you build the executable for being uploaded on a hardware which is not connected to any, let's say, serial terminal, then you don't have to use the standard input-output library. You can avoid to include in it. Okay, so very, very simple. Let's come back here. Okay, now let's see another application which is a little bit more interesting, and it basically do the same work that the Blink application in TinyOS did. So we have a timer which fires and trigger the switching of LEDs. And in this case, we will use two different processes. So we will have, let's say, a look at how we can manage two processes in one single application. And we will use, let's say, a slightly modified version of this Hello World application that we have just seen, which basically starts a timer, and each time the timer fires, it prints Hello World. So one process does this kind of implements this logic, and the other process, which is the Blink process, starts a timer, and each time the timer fires, increments a counter and toggles the LEDs according to the value of the timer, of the counter. Okay, and we will see it also in Kuja what happens. Now this the source file for this example will be uploaded as soon as possible on the website, so you can use it. It's here. Okay, now as you can imagine, here we are working with LEDs, okay, which are a part of the hardware system, right? So in order to use them, we have to include the proper, let's say, library, okay? And in this case, the library is this one, dev/leds.ah, which contains all the functions that can be called on the LED interface, okay? And again, on the documentation you have all the information how to use these and other libraries as well. Now the interesting thing is that we declare two processes now, okay? So we have two processes, one which is the Hello World process, and this is its name, and the second one which is the Blink process, and this is its name, okay? So an application which is composed by two processes. And we require the two processes to start automatically at the beginning, okay? So in this case, all the two processes will be started at the beginning, but you can also have macros for starting one process from another one, okay? Meaning that you can start just one process, and then at a certain point you can decide to start or stop another process, okay, depending on what you need to do. So this gives you a little bit of flexibility. Now the first process, which is basically a slightly modified version of the Hello World process, we have a timer, okay, here, and a counter. Now the timer is a particular object, let's say variable in Contiki that of course allows you to use a timer, just as we used timers in TinyOS. And so we have the two macros, process begin and process ends here, and in between we have the source code, right? So first of all, we basically set the timer using this function call, the timer set. We use the timer object, this one, and we set the timer to generate an event in 1 second. This is let's say defined constant to generate one event in 1 second. At this point, we enter our infinite while loop, okay? And the first thing, we wait, meaning that we have set the timer, now we want to wait for it to fire, okay? When the timer fires, so we have basically to check what kind of event was returned, okay, by the operating system. And these variables here stores the type of events which are triggered by the system. So here basically we check if the event is in fact the timer which was expired, because if you just use this macro, your process will wait for any event which is triggered, okay? So if you have different events which can be triggered, then you have to check which one was the cause for your waking up. So if in this case is the timer, then what we do, we have to say, okay, let's just print hello world and the value of the counter, and then increment the counter, okay? Then what you have to do, just as in Mode Runner, you have to reset the timer for another event, okay? It's not like in TinyOS that you have the periodic command on the timer, so you can just call it once and then the timer will always reset itself without any need for your manual reset, okay? So we are here in this infinite loop, and each time we will, get the event, print this, and then reset the timer. So this will print hello world once per second, right? And this is the first process, this one. Now the other process, it's a completely separate piece of code, right? Which is the blink process. It has its own events. It has its own timer. Now it's called the same, but it's a completely different timer from the other one, okay? And you have, in this case, a variable which is the LED state. And then you have your infinite loop again. So you set the timer. This time is 250 milliseconds, so 4 Hertz basically. And look, here we are using a different macros, so basically we are waiting exactly for the timer to be fired. So we are not using just wait event, but we are using this other macro, which is wait event until, and we are checking the condition inside the argument. So this macro basically it's combining these two statements here, okay? So this macro will wake up your process only if the event is in fact a timer event, okay? And here you can put basically any condition that you need. And of course, what we will do then, we will turn off all the LEDs and we will turn on the LEDs based on the counter, okay? And then we will increment this. So we will swipe all the configuration of LEDs from all off to all on, okay? And then the process ends. So two different processes that are started automatically by the system, okay? Let's try to run it. We can create a new simulation. Create a new sky mode. I'm going to Blink folder, compile. Will take a little bit. Yeah, it's a little bit slow. It will be for sure faster on your PCs. But this is probably due to the make file here, right? Yeah, no, it's okay. Well, anyway, let's wait till it finishes. Because it's compiling also all the libraries of the system, so probably there's something in the makefile which tells to compile everything which was already compiled. Okay, create the mode. We add the mode. We start the simulation. Let me just put 100% of speed limit. And as you can see here, I have all the prints here, hello world, with the counter which is incrementing, and the LEDs. And if you remember, yeah, we can show LEDs by doing this, and we have the LEDs that are blinking, okay, according to the code. So it does exactly the same as the blink application that we have seen in TinyOS, but with a complete different approach. Good. Come back here. Now, regarding the simulation environment, well, we have already seen it, just a couple of words on it. So, it's a network simulator. Now you know that we can simulate several nodes. Each node can have its own process. So it's not like in TOSIM that we have all the nodes in a simulation which run the same application, but here we can decide to create, for example, 10 nodes with a particular process on top and other nodes with another process, and we can see what's the interaction between the two applications. We can also simulate different types of modes in terms of hardware. It's graphical, so it's nice. We can save a node simulation in order to then, not to recreate simulation environment anytime. And we will see other features when we see network communication. In particular, we will see how to change the communication range of nodes, change the transmission parameters such as the probability of success in a transmission and this kind of stuff. Now, just a very, very brief explanation of why using proto-threads in Contiki, and so why moving with that style of programming which is different from what we have seen in TinyOS. Now, what the authors of Contiki claim is that using proto-threads leads to a much easier to understand source code, basically. So using proto-threads is easier than using a state machine, such as the one you have in TinyOS. In TinyOS, you basically, if you have a complex application, you have to track the status of your application because you have events that are triggered, and you basically manage these events always in the same way because you have block of code for managing events. Now, if you have to manage these events in different condition of the system, then you have to keep track of what's the state of your system. Okay. Put it in another way, when you receive a message in TinyOS, you will always execute the piece of code which is inside the receive event, right? Now, depending on the state of your application, for example, if you are in an initialization phase or if you are in a particular state, the source code which is inside the receive event must be differentiated, meaning that most likely you will have a switch case statement that checks for a particular status of your application and runs a different code for managing the received message depending on the state, right? And these may produce very long piece of software, okay, because you have to manage all the possible states of your application. Instead, by using proto-threads, you have let's say code which is generally shorter and thus it's much easier to understand, and the logic mechanisms are evident from the source code, while it's not that easy to understand them in TinyOS. Now, if this is true or not, I guess that it depends on the background of the programmer. So it depends a lot on what the programmer is used to do, okay? Just an example, imagine that you have this sort of logic, okay? So you have basically three states in which you can be: the on state, the waiting state, and the off state. And what happens is that if you are in the state on, then you have to do something. If you are in waiting, then you have to do something else. And if you are in off state, then you have to do something else again. Okay? And in order to write the proper logic, you rely on this some sort of state machine that tells you what you have to do depending on the state. Okay? And you see that you end up by writing an event handler, so a source code which is executed when an event comes, and inside it you check the state in which you are, and depending on the state you do something which according to what the state machine tells you to do. Okay, and this produces this, let's say, long piece of source code. The very same stuff can be done in Contiki just by writing this code. So the state machine is the same, the logic is the same, but the source code that you use is much less than before, and the logic is, the mechanisms are evident from the source code. So what's happening? Okay, so you are on state, then you are in wait state, and then you are in off state. Okay, and this is a while loop. So one of, let's say, the main claims of the authors of Contiki was this change of programming paradigm, which can ease up your life as a programmer. Now, I'm not completely sure about this statement, okay? Mostly because my experience as a programmer was basically was mainly on TinyOS, okay? So I worked for several years on TinyOS, and moving to Contiki was a little bit, let's say, it took some time, okay? Just because the programming styles are very different. So I guess that it depends from where you start, okay? Good. Now let's move to communication, okay? So we have seen very quickly how to set up an application, how to start it, how to also already debug it with print statements. We have seen how to use hardware, basically LEDs, and in order to do that you have to include the proper libraries. Now we will see how to send messages between nodes, okay? Just as we did for the other operating system. What I will show you is just the lightweight communication protocol, which is RIME, which provides primitives for transmitting messages in different configurations. So you have unicast, reliable unicast, and broadcast, okay? For reliable unicast, I mean that you have acknowledgement back, so you can know whether the message was sent or not, and you can react properly in order to be sure that the message will be delivered to the destination. We have both single hop unicast, meaning transmission from point-to-point transmission, and multi-hop unicast, meaning that you can set up a routing tree and the destination can also not be in range, but for reaching it you have to pass through several intermediate nodes. Okay. Now, the routing policies are up to you, so it's you that decide what kind of routing policies you should use, if using the shortest path or other kind of policies. Okay. And it also provides some primitives for network flooding, meaning for disseminate a data from a central point to all the nodes. This is called flooding. And also the reverse process, which is data collections. So from all the nodes to a central point. Okay. So with RIME, you have already implemented these two very useful primitives, and that's why I guess you find Contiki as a starting point for many commercial applications. Because at the end of the story, if you think about it, many commercial application requires either to do flooding or to do data collection. Okay, you have several sensors around, and then at the end you want to collect data from them. So if you already have something that you can run off the shelf and does data collection, then you are okay. Okay, you don't have to spend hours in implementing your own collection protocols. So we will see in a minute an example on how to use this RIME protocol. You have to declare what kind of communication you want to use. For example, this is the case for broadcast communication. So a message which is transmitted on the air and everybody can hear it. So you have to declare an object, basically a variable, which is of type broadcast connection. Okay, and then you have to open it on a particular channel, which is again similar to the AM channels in TinyOS. So it's or the TCP ports in TCP. So it's a particular channel which is not the frequency channel that you use, but it's a logical channel that you use to differentiate messages, let's say. And you have also to pass a function pointer, so a pointer to a function which will be executed when you receive a message. Okay, and this is similar to what happens to delegates and callbacks in Motrunner, but it's different to what happens in TinyOS, where you have an event which is up there and you have to implement it for managing messages. Instead, here you explicitly write a function, and then you pass the pointer to this routine, and this routine will call that function when a message is received. Okay. We will see how to set up the callback. So the mechanism is very, very similar to what happens in Motrunner. Instead of seeing this, let's go directly to the example, which is in RIME. Now, if you go here in RIME, you have several examples depending on what kind of protocol you want to use. Okay, so you have collection, mesh network, multi-hop, reliable unicast. We will see the broadcast example. Okay. So it's a very simple application which each mode will broadcast a message, and when received they will write, okay, I have received a message from this particular mode. RIME also provides some sort of addressing, which is very similar to the ID of TinyOS. Okay, so each node, when you use RIME, each node has an address, which is basically a number 2 bytes number, so from 0 to the 16 minus 1, and you can refer to nodes by using that ID basically. So let's see this application. In this case we are using the RIME service, so we have to include RIME here, okay? And we are also using well, some other libraries like the button, but this is not interesting now. So I declare only one process this time, the example broadcast process, which will be started automatically at the beginning, okay, with the auto start macro. And then this is the function that will be executed when a message is received. Okay, so it's the function that will be called automatically when a message is received. And what it does basically, it will write on the terminal broadcast message received from, and then I will write the RIME address which is inside the packet that I have received, which is this one. And then I have this is basically the statements for setting the callback. So for actually saying that this is the function that must be called when a message is received. Again, the thread, it's here between begin and end. We have a timer for sending messages. When we have also a macro for saying that when we exit the application we have to close the broadcast component, basically broadcast connection. So basically you release the memory which is associated to it. And so first of all we have to open the communication. This basically is the equivalent to the radio control.start command in TinyOS. So it opens up the radio, and of course it puts the radio in working mode. Then I have my while loop. I will set a timer, this time with a random clock, so between 2 and 4 seconds, just not to be completely synchronized. Then I will wait until the clock expires, and what I will do, I will copy this string inside my packet payload, okay, and then I will transmit with broadcast send my packet, okay, and I will print message sent. Now there's I would say a clear difference here with respect to MoteRunner and TinyOS. Can someone spot it? It regards basically how the packet is prepared. Do you remember how to prepare a packet in TinyOS or in MoteRunner? Anyone? So in both cases you have a variable. In TinyOS is a message t variable, in MoteRunner is an array of bytes, okay, that you have to fill with data, okay, but you have a variable in your program, and that is your message that you will be transmitting. Inside here you don't have such a thing, okay, so you do not have basically access to the variable that contains the payload of the message, okay, but you have a function to fill the payload of the message that then RIME will transmit for you, okay, so it's somehow shadowed, okay, you don't have direct access to this payload, while in TinyOS and in MoteRunner you have. And you can just modify the payload by using the copy from Okay, so moving bytes from one part to the other one. Let's simulate it. We can create a new simulation. Sky mode. Let's go to the rhyme here. Sorry. This one. Okay, we have to wait a little bit, I guess. Oh no, okay. So I will create two nodes, okay, which will be added here. And if you go on view and you select the radio environment, and let me just zoom a little bit. Okay, so we are using the unit disk radio environment, and if you remember, the green part is the part, let's say the range where you can receive messages. So if node 1 is inside the green range, then it can receive broadcast messages. The gray part is what is called the interference zone. So node 1, if node 1 is in the green part, in the gray part, it cannot receive messages from mode number 2, but other messages from other modes will interfere, okay, with the one sent from mode 2. So node 1 cannot receive messages from other modes if it is in range here. Well, it's not that it cannot, they will interfere, okay? Now I will put the two modes in the same communication range area in order to have communication between them. And okay, I will start. So this was started, and then as you can see, I'm receiving messages, okay? So I have the content of the packet and the source address. Now what happens if I move them away? They will transmit messages, so I will see broadcast message sent, but no one will receive, okay? Because they are out of their communication range. If I take a node and I put it back here, then they will start receiving them again. Another interesting thing is that if you click with the right button of your mouse, you can change both transmission ranges, so you can change the size of this green and gray circle, and also the transmission and reception success ratio. Okay, now it's 100% for both transmission and reception. You can make it maybe go down to 50%, and in this case this is for mode 1, so mode 2 will not receive basically half of the packets which are transmitted from mode 1. Okay, so you can modify your simulation by changing the parameters here. Okay. So as I was saying, we have also other examples, and you can try to use unicast, reliable unicast, multi-hop communication, and this kind of stuff. If you need more complex network protocol, then you can use the micro IP stack, okay? And this will provide IP addresses for your nodes, will provide TCP control for your modes, for your messages, and this can be useful if you want to connect your sensor network with an IP network then, okay? So you don't have to translate everything from IP to your own protocol, but you can directly use IP, okay? So you can, for example, use COPE for requesting data from sensors directly from an IP network and all this kind of stuff. Okay, as a final tool, we will see how to attach Contiki to Node-RED, okay? So we have seen this for TinyOS. You have also the code on the website, both for the new virtual machine which contains Node-RED and also the flows that you can import in Node-RED in order to read from a simulation in TinyOS. And well, in Contiki is much more easier since we already have the printf statement which is printing on the serial port. We will just intercept all the text which is output from Kuja basically. So again, let's see an example of this. I will open the, so first of all I have to open Node-RED, and you can do this by just typing, if it works. Oh, it's so slow. Let's pause the simulation at least. So you just started by typing Node-RED here. Okay. Then you go on your browser Oh my god, it's so slow. And you go on localhost at port 1880. So basically what you have to do is to intercept messages from Node-RED, from Kuja, and in this case Kuja has its serial communication port on this one, 60001, and if you click here, so we will connect to this port at localhost since both Node-RED and Kuja are running on the same machine, and what we will output is a stream of string, and each string is delimited by the string terminator basically. And if you run your own, let's say, application, you can decide that your strings will be terminated by a particular code, so then you can intercept strings from here. Okay, so if I deploy this, it's already deployed. So if what you have to do is to open the serial socket here on the node that you want to intercept messages from on the server, and you wait a little bit, you will see client connected. The client is now Node-RED, which is attached to Kuja. If you start this, Kuja will start sending all these print statements directly to Node-RED. Okay, so if you go into Node-RED, you see, we see the same strings that are appearing in Kuja. Now from here you are on the web, so you can parse these strings, whatever this string contains, for example data from your sensor network, and then you can use the other functional blocks of Node-RED for treating this data as you wish, doing processing, storing, doing, plotting graphs, everything you want. Okay. Instead, if you remember for TinyOS, so by running a TinyOS program into Kuja, you have a particular function here that you have to insert in order to parse messages from TinyOS. It's not that simple. Okay. I guess that's it. Let me check on the slides. Yes. So that's it for today. We finished it a little bit earlier. Any questions? Okay, so of course we couldn't go into all the details of Contiki. If you are interested, of course the suggestion is try to play a little bit with it. Try at least to run the examples that you have and see what's happening. Change a little bit of parameters, maybe see if you can get something interesting out of it. And we will see next time that for the projects, my suggestion is to use TinyOS, just because we have seen it a little bit into details. But of course, if you want to use Motrunner or Contiki, you can. Okay, so it's up to you to choose what kind of operating system suits better your application needs. Okay. And also, if you do not want to do one of the projects that are listed on the website, but you want to do your own project, again, you can use whatever you want. Okay? Um, very good. So I think that's enough for today. We'll see you next week.